Markovnikov's and AntiMarkovnikov's rule. To understand the concept of Markovnikov's and AntiMarkovnikov's rule, we need to learn some basic concepts such as pi electrons. And look at this alkene, it contains one double bond, and this double bond is comprised of pi electrons. We all know that these pi electrons are loosely bound to each other. So if we bring an electrophile close to this pi bond, it can readily attacked by an electrophile to form a carbocation like this. And this CH2 will get attached to H positive and another carbon will acquire a positive charge. So that is known as a carbocation. Clear? Secondly, symmetrical and unsymmetrical alkenes. Look at the first example. It contains two carbon and there is a pi bond between these two carbon. Just look at the number of carbons at the left side of the double bond and the right side of the double bond. There is one carbon at the left side of the double bond and also on the right hand side. So it means it is symmetrical if the number of carbons are same on the left side of double bond and the right side of the double bond. Then it means it is a symmetrical alkene. So take another example. This is your compound B, and in this case, the number of carbon on the left side of the double bond, there are two carbons, and on right hand side, there are also two carbon. Then it means it is also symmetrical alkene. Symmetrical alkene. Okay. Then take a look at the third example. In this case, there are two carbons on the left side of the double bond and the one carbon on the right hand side of the double bond. So the number of carbons are different on the left side and the right hand side of the double bond. That's why it is known as unsymmetrical alkene. Unsymmetrical alkene. So this is the basic difference how to identify symmetrical and unsymmetrical alkenes. Just count the number of carbon atoms on the left hand side and the right hand side of the double bond. Then if the carbon atoms are different, it means that is unsymmetrical alkene. The third is carbocation. Clear? We all know about carbocations. If a carbon has 6 electrons in its valence shell and the carbon acquires positive charge on it, then it is known as carbocation. As this is your primary carbocation, in this carbon is linked to one alkyl group. That's why it is primary carbocation. And this is your secondary carbocation. In this, the carbon acquiring positive charge is linked to two alkyl groups, and this is your tertiary carbocation. In this, the carbon is linked to three alkyl groups. And among these, which is more stable, tertiary carbocations are more stable as compared to secondary and primary because of inductive effect of alkyl groups and hyperconjugative structures formed by these alkyl groups. So these are the two main reasons. First is inductive effect. The second one is hyperconjugative effect. So tertiary is more stable than secondary than primary. Similarly, this is true in the case of free radicals. Okay. So this is your primary free radical. In this, the carbon carries a one electron here. And there are 6 valence electrons in its valence shell. And this is secondary carbon free radical. And the third one is tertiary free radical. In this case also, tertiary is more stable than secondary and primary. Clear? Okay. Then the fourth one is hydrogen halides. Hydrogen halides, when there is bond between hydrogen and halide. It is known as hydrogen halides. The first one is hydrogen iodide, hydrogen bromide, hydrogen chloride, and hydrogen fluoride. Out of these, which is more easily can undergo reaction? Because the bond between H and I is more weak, so the HI can undergo the reactions easily than HBr, then HCl and HF. So you can say, in other words, HI is more reactive. Just a sec. More reactive as compared to HBr and HCl and HF. The reactivity depends upon the bond strength. Clear? Okay. The bond strength HF. In this, the orbital used are 1s and the fluorine is using its 2p orbitals. Clear? And but in case of HCl, the bond is formed between orbital 1s and 3p. And in case of HBr, it's 1s and 4p. But in case of HI, the bond is formed between 1s and 5p. So as the value of N is increasing, the bond is going weak. The bond strength is decreasing because because the size of the halogen is increasing. This is the bond between HF and uh, the overlapping between HCl looks like this, and the overlapping between HBr is look like this, and HI is like this. So bond between these two is very weak as compared to relative to other halogen as halogen halides, hydrogen halides. So that's why HI is more reactive. Yeah. So moving toward Markovnikov's and anti-Markovnikov's rule. Okay. Clearly, first of all, Markovnikov and anti-Markovnikov rules. These are clearly observed in case of only HBr. When HBr is added to the alkene, which is unsymmetrical in nature. Clear? You have to remember this point when the alkene is unsymmetrical and you are adding HBr, then you will get two kind of opportunities. One is the addition through Markovnikov's rule, another is the addition through anti-Markovnikov's rule. Clear? So I have taken an unsymmetrical alkene. This is your unsymmetrical alkene. In this, the HBr is added. HBr is added via electrophilic addition reaction. In the first case, there is only the reagent used is HBr. Okay, then you are getting the product 2-bromopropane. The bromine is added over this carbon. But in second case B, you get the product 1-bromopropane and the bromine is attached to carbon number 1. So this is the possibility B. But in second case, the HBr is used along with benzoyl peroxide. Clear? So why you are getting two different products? You are adding HBr. In first case, it is simple. The second case, you are also using benzoyl peroxide. So what is the difference between both of these? In first case, A case, the Markovnikov rule is used. But in second case, the addition is done according to anti-Markovnikov's rule. Clear? Okay. So why there is a large, huge difference between both of these two? Let's understand this by mechanism. So in first case, Markovnikov's rule, negative part of the halogen acid. Halogen acid means HBr. H carries partial positive charge and the bromine carries partial negative charge due to the electronegative difference between these two atoms. Bromine has electron withdrawing nature, so it will require partial negative charge on it. That's why it is known as the negative part in halogen acid. So the Br negative, it will attach to that carbon which have less number of hydrogen on alkene. Clear? Okay. So look at this alkene. The carbon number A, it has one hydrogen, and the carbon number B, it has two hydrogen. So according to Markovnikov rule, the negative part means Br negative, it will attach to the carbon number A because it has only one hydrogen. It has less number of hydrogen as compared to another carbon. So you will check the number of hydrogen which is linked to alkene. So this alkene, clear? So that's why bromine is attached to carbon number A. This is the addition according to Markovnikov rule. So it is the saying of Markovnikov rule. Why Markovnikov rule is applied according to this way? Why the negative part is attached to the carbon having less number of hydrogen? So coming to the mechanism part, the first is the dissociation of HBr. The HBr is dissociated into two parts. That is, first is H positive, another one is Br negative. The second step. Okay. In second step, I have shown two possibilities and represented it as A and B. In first case, A. Hmm? There is formation of a carbocation. Okay. And there is shifting of these pi electrons from atom number, you can label it 1 and 2. From carbon 1 to 2, the electrons are shifted toward carbon 2. Clear? Okay. When the electrons are shifted toward carbon number 2 will get negative charge and 1 will get positive charge. Clear? Then after that, the electrophile will attack on this negative part and the second carbon CH2 negative will be attached to H positive forming CH3. And again, the carbon number 1 will acquire the positive charge. So thus, your carbocation is formed as intermediate. So you have to identify what kind of carbocation here it is. This is your secondary carbocation as this is linked to two alkyl groups. Okay. In second case, when the pi electrons are shifted to from second carbon to first carbon, when the pi electrons are shifted from second carbon to first carbon, the first carbon will get negative charge and the second carbon will get the positive charge. Again, electrophile will come. Okay. Then it will sorry, attack on this negative carbon and it will form, yeah, just wait a second. Okay, then it will form the intermediate which is primary carbocation. And look, the carbon having positive charge, this is primary in nature because this is your one alkyl group, two hydrogens are there. So the major product is formed due to the secondary carbocation. As we know, secondary carbocations are more stable than the primary carbocation. That's why the second possibility is not happening over here. The first possibility is taking place. According to first possibility, the bromine will be get attached to this carbon and you will get 2-bromopropane as major product. So what is the reason in this case? In this case, carbon cation is forming as intermediate. You will explain by saying that the carbocation which is more stable, the product is formed according to the carbocation which is more stable in nature. So this is your Markovnikov's rule. The negative part will attach to that carbon which have less number of hydrogen on the alkene. Okay. Then anti-Markovnikov's rule. In anti-Markovnikov rule, the mechanism followed is very different. The mechanism followed is through radical formation. In this case, the radical is generated. So why in this case the radical is generated? Because of the presence of benzoyl peroxide. In case of anti-Markovnikov rule, we are using benzoyl peroxide as well. Okay. Okay. This anti-Markovnikov rule is also known as peroxide effect, because this is your peroxide, as well is this is also known as crash effect. Crash effects named with the scientist Crash, that is named as crash effect. And anti-Markovnikov rule, it is just opposite of Markovnikov rule. In Markovnikov rule, negative part is going toward the carbon having less number of hydrogen. In this case, negative part is will be attached to that carbon which have higher number of hydrogen. Then going back to the previous example, so just look over here. This product in this bromine is attached to carbon having two hydrogen. Clear? So the addition here is according to anti-Markovnikov rule. So just understand the concept of anti-Markovnikov rule through the mechanism. The first step is your initiation step. In initiation step, what happens? The free radicals are generated as there is a peroxide. Which kind of peroxide is this? This is your benzoyl peroxide. Okay. Okay. So this oxygen will get its own electron toward itself, and this oxygen will attract its electron toward itself. So it will lead to a homolytic fission over there. When there is homolytic fission, each individual atom will get its one electron towards itself. Okay. Then you will get a benzoyl radical. This is your benzoyl radical, one molecule, and this is your another molecule. So you are getting two molecules of benzoyl free radical. Again, there is a homolytic fission, and these two are forming bond with the release of, just a sec. Yeah. With the release of carbon dioxide, there is formation of phenyl free radical. Similarly, another molecule is also forming a phenyl free radical with the release of carbon dioxide. Yeah. Okay. Now, this phenyl radical is reacting with HBr, then again generating benzene and bromine free radical. So initiation steps are those steps in which there is formation of free radicals. Okay, the third one step is known as propagation step. Okay. So during the first step, a bromine free radical adds to double bond in such a way to give more stable free radical. I have shown here the both possibilities in which there is addition of bromine free radical to carbon number 1 and carbon number 2. When the bromine free radical is added to carbon number 2, then it generates a free radical which is secondary in nature. In case B, the bromine free radical is added in the way to carbon number 1 and generates primary free radical. So as we have already discussed that secondary free radical is more stable than primary free radical. So the major product will be formed via this free radical. Okay. So this is your secondary free radical. This free radical will be attacked by hydrogen H radical and thus formed a bond between carbon and hydrogen. This is your 1-bromopropane. So this free radical abstract H radical from HBr to complete the addition. Clear? the major product is 1-bromopropane. So according to Markovnikov rule, you are getting 2-bromopropane, but in this you are getting 1-bromopropane. So you have to remember the first condition is HBr. This is only true in case of HBr. The second is, remember, look the conditions whether the benzoyl peroxide or any another peroxide is present in the reaction or not. If peroxide is present, then it will follow anti-Markovnikov rule. Then you can just write the product without knowing the mechanism, because according to anti-Markovnikov, this CH2 has more number of hydrogen, and the bromine is linked to this part. Clear? So just by remembering the rules of Markovnik and anti-Markovnikov rule, you can get your products easily. Okay. Okay. Then yeah, if we need to add HCl, HI, and HF, HBr to this symmetrical alkene, then the product you will get is CH2, Cl, CH3, CH2I, CH3, CH2F, CH3, CH2Br. Because this is symmetrical alkene, the hydrogen or either halogen can be added to either carbon. Well, the problem arises in the case of unsymmetrical alkene. In case of unsymmetrical alkene, if the rule is followed, Markovnikov rule, means there is no benzoyl peroxide effect. Okay, then you will get the product as secondary halogen substitution. Okay, then the halogen will be substituted at the second carbon. This is your carbon number 1, 2, and 3. You will get this product. Okay. So if you are using benzoyl peroxide in the reaction and the alkene you have is that is unsymmetrical, and this is possible in the case of only HBr. Why HBr? I will discuss it later. Okay, so just I am showing the energies of propagation step over here. This is your HF, HI, HCl, and HBr. In propagation step, there are two steps. The first step is addition of bromine radical. Clear? Okay. And the second step is addition of hydrogen radical. Okay. When there is addition of bromine radical, the energy released in case of HF is minus 209, because this is exothermic step and there is a negative sign, the energy is too high. Okay. And when hydrogen radical is added, its energy is endothermic, that is 159. And in case of HI, the first step is endothermic, the second step is exothermic when hydrogen radical is added. And in case of HCl, it's the first step is exo, second is endo. But in case of HBr, both the steps are exothermic. The heat is released in both cases. Clear? So that's why this effect is possible in the case of HBr. Clear? In case of HF, there is strong bond between hydrogen and fluoride. So it's very difficult to break this bond. So that's why large energy will be released. That is high, minus 209. Minus sign is used to represent whether the reaction is exothermic or endothermic. If there is minus sign, it means it is exothermic. If there is a positive sign, then it is endothermic. Okay. Okay. Then now look at the HCl. Again the bond between HCl is very strong. Okay, then the bond between HBr is not too strong, not very weak, so it can be easily broken. So the energy released is 42. But in case of HI, the bond breaks very easily. When the bond breaks very easily means iodine is added to the alkene very readily, but this is not enough energy to add H positive radical in the second step. In case of HF, the first step is exo, the second is endo. In case of HI, endo, exo. So one step is exo, another is endo in case of other halogens. But in case of HBr, both the steps are exothermic. When you will look at the overall sum of these two energy steps. Okay, so you will get the result in case exo. This is also your exo, and this is your also exo. Clear? But the energy is not sufficient to take place the another steps. Yeah. So that's why peroxide effect or crash effect and anti-Markovnikov effect is found in case of HBr. So this is the reason the other halides do not behave as same manner as HBr, because in case of HBr, both the steps are exothermic. In other halides, one is exo, another is endo. So that makes the addition of either either addition of halide radical or H radical difficult. So basically, radical chain reactions are successful only when propagation steps are exothermic in nature. So both steps should be exothermic in nature. So this is a history behind this is a theory behind Markovnikov and anti-Markovnikov's rule. Clear? Okay. Thank you. If you have any query, then you can ping me in the comment section and ask any kind of question. Thank you.